And just a little bit about my background. I got my degree in industrial design, and I have specialized in mass manufacturing consumer products, mostly electronics, IoT, and home and kitchen organization. I work both with products that I design or I get someone else's design and convert it into a scalable product. And that's pretty much what I do here at the lab too. I assist the teams with their projects, and also I design and develop a few products in-house for the company. All of that while I get to use the awesome equipment that we have here at the lab. So yeah, pretty stoked to be here, hear about your projects, and let's get it going.
Perfect. Thanks, Gio. Kevin, if you guys want to start, you can go for it.
Sounds good. So we are representing the small cat team. I am Kevin Harrington, Cam Bislin, Xavier Little, and we've been working together to solve a particular problem. So dynamic style walking where robots know whether or not they're falling over and being able to compensate, is a hard problem, but a very important problem to solve. And we've noticed that there's a chicken and the egg problem here in terms of the availability of hardware and the education necessary to learn how to run that hardware. You need the hardware to learn on, you need an education to run the hardware, and without both existing, neither has been able to come and exist in the real world. So we see our solution as SmallCat, a piece of hardware that is capable of doing dynamic style walking, as well as Boulder Studio, a programming interface for programming the cat, and a partnership with Worcester Polytechnic Institute, a robotics engineering university that will help us spread the method, spread our curriculum throughout the world. The plan for us is to work with the university to sell classroom kits. So the kit would contain all the hardware necessary to build a set of small cats. We have spec'd out 25 cats per classroom, would allow project groups to work independently with their hardware to develop an understanding of how quadrupeds work, while at the same time having hardware that they can validate their learning on. Because we were partnered with WPI, a test class of this type, that learning how to run robots with this cat, will be run here at WPI starting in October. And then from there, we'll refine the teaching materials and start working to publish it more broadly, initially marketing towards undergraduate universities throughout the United States, of which there's 80 programs, none of which have the type of class that we are offering, none of which have the kind of hardware at the price point that we're offering. And we can also look to expanding our ability to provide value to the market, not just in the kits, but also teach the teachers, where you do remote sessions such as this, our educators. We have demonstrated this with the Maths and Science for Sub-Saharan Africa, the M4 SSA program here. Guy. Hi, Darren. All right, cool. Keep going. We've done Maths and Science for Sub-Saharan Africa, where we're teaching educators across Sub-Saharan Africa how to design and build robots. This would be sort of a next level program for not only that market, but also the university markets throughout the United States. We see also expansion into graduate programs, more complex actions, and we have more sophisticated hardware to meet those graduate programs in the pipeline, as it were, in terms of products. So this isn't just a singular product, it's a product line with a common educational framework and a common computation system that runs all the different cats. What we see here is an opportunity that is not being met by the existing market competitors. Boston Dynamics obviously solved the math problem, but then does not teach anyone how to do it. They keep that as a proprietary black box for their company, and they're actually selling the service of that system. So the target market that we're looking to serve that wants to teach this is not served by that competitor. On the sort of opposite end, the Nibble Cat, which has been very popular on Kickstarter, is not capable of doing the kind of dynamics that this platform is capable of. It also is not geared towards teaching materials. I don't know if anyone's actually gone through them. They're not there yet. An emerging skill, let's say. And in terms of competitors, the market is very thin in this education market. The Sony Aibo might be another example of a quadruped in the market, but that's more social robots. That's, again, not targeted toward the teaching. So as educators, there's not a single solution in the market for them to solve this problem. And we see taking the research-grade robotics engineering, the world-class education of WPI, and novel hardware that we've developed here as part of our studies at WPI, my job here at WPI, to make it possible to teach dynamics-oriented walking to college-level students throughout the world.
Makes sense. I mean, I think the closest model I've seen is Sphero, and that seems to be a lot of like the guiding methodology that you guys are working off of. And I think this is the next logical step because like Sphero is awesome. You get to play around with it and it's programmable, and it seems fairly successful in an educational environment for younger kids, but you're just trying to address that on the more adult front. And I think that there is a growing appeal to that. And certainly, yeah, Boston Dynamics can't come close. So,
right. Boston Dynamics will never compete on price and also wants to keep their stuff proprietary. That's
exactly.
The model is they have a trade secret and they're going to keep that and keep pushing the boundaries. They are the most impressive dynamics-oriented quadrupeds on the planet at the moment. But that's only because nobody else knows how to do that. And anyone that would like to learn can only learn on simulations, and simulations, you know, as any roboticist, they're only so valid. As we learned ourselves, our simulations work better than the physical model, so we're always using the data that we get from doing this development to feedback into our models.
Cool. Well, first of all, congratulations for getting all the likes.
Thank you.
Now, I hear about your concept, and I should probably mention that the main objective right now is to talk about the process when you try to scale your project. You know, two of the criteria for this year, as Magenta said, we are upping the stakes, the challenge. One of them is, well, you talked about the concept right now, but we have two other important ones, which are design and production. So I wanted to hear what challenges you have about, you know, how you plan to scale, because that's something that in the past we didn't need to mention. You know, if we had a really cool concept and as long as it worked, that was pretty much what you needed. Yeah. It worked. No, but now it comes with a plan. You know, all that you mentioned about having the robots at schools, not only in the US, but abroad, that's a very ambitious and awesome plan. So how do you plan that? And are there any roadblocks that you're facing? Let me hear about that.
So the primary plan for production rollout is to start off acknowledging that our market is initially small. In order to service that small market without drowning ourselves in capital costs, maintaining designs that are designed for 3D printability. Grab it so they're not buzzing in the speaker. Actually, here. While we talk. I mean, adorable is really part of the thing. So, so the purpose of the design for manufacturability is looking at 3D printing as the primary production medium. We've also engaged with a engineer who did the resin cast molds for Hasbro for a while, making their prototypes for injection molding production. We don't think that we're likely to hit the scale of injection molding with the current iteration of the design. So the highest volume production we're likely to hit is actually going to be well served by the resin casting model, where we take the 3D printed parts, we create a series of resin casting molds. From those, we create master molds, and then we'll have soft molds to cast hard resin parts at well above the scale of that we're expecting to see. So we imagine if we have 12 customers with a 4-year turnover cycle, every 4 years we would sell them a new kit of robots to sort of swap things out. Whatever the new version would be, we see that as a continuing revenue stream. The goal is then to say, if we hit 12 customers, we're at break even in terms of our overhead costs and salaries of the engineers necessary to run this operation. That being said, I'm also an employee here at WPI. I don't need this as a primary pot boiler. This can be an additional business that WPI is very interested in supporting their staff and faculty as part of entrepreneurial processes. They like seeing that happen, so the more that happens, the better. So we would see 3D printing with our own set of printers. It's designed to be printed on the Lulzbot TAS 6, although maybe we would go with the Lulzbot Pro since it just did come out.
Or the Prusa, potentially.
Or the Prusa. And the use of the capital would be to build out our production facility, pre-purchase some component stock, get ahead of those ever-shifting tariffs, as we know. Make sure that we have enough components on hand to service our need for the upcoming year, and then operate using lean manufacturing. We've been using an ERP software for managing components, kits, kit cost, manufacturing efficiencies, and doing operational predictions over a long period to see what that would actually look like in terms of our unit and production cost, and then our sort of at what point will we need to upgrade the capital, and then at what point do we then need to upgrade the design for an even more upgraded capital. Let's imagine we're more wildly successful than we could imagine. This design could be reimagined, at least at the mechanical level, to be injection molded. Although right now, the effort and tooling costs, especially of design for manufacturability in that volume, doesn't make sense for the market that we're targeting.
All right. So for me to fully understand, the first iteration would be with 3D printers. Then as you increase volume, you would move to resin casting.
Yes.
And then eventually you would move to plastic injection.
On the electronic side, we're going to go directly to full-turn manufacturing because that's easy enough to prototype. We do have an electronics manufacturing tools here at WPI, so we're going to be doing very rapid iterations over the summer. And then the final deliverable will be a kit of as many commercial off-the-shelf multi-vendor source components as we can find. Then anything that we need to make custom will be full-turn, just pay money, get a work in progress component, put it into the kit, and call that done.
How many cats can you print, or robots can you print with a single TAS per day, or how does it work?
One TAS, one cat, one day.
One TAS, one cat, one day.
And the assembly of the full cat takes probably about 2-3 hours to put all together once you have the parts and pieces.
Right. So we would hit sort of saturation point at if we're doing 8 cats a day with one person doing assembly. That being said, the way this is structured is the assembly is actually part of the lesson plan. So the students would be doing that assembly, and then at the end of their class, they would disassemble the cat for the next team. Which means from our labor costs, we print the parts, we put them in a box, we buy the raw materials, we put them in a box, we put a CD or a flash drive with all the educational components in the same box, and it goes out the door. So marginal cost labor is 4 or 5 minutes of unskilled labor.
Cool.
And the second would be the same concept as that.
we take the Turtlebot 3 as a price point and sort of use case example, targeting the very similar markets, but teaching a very different set of concepts. The Turtlebot 3 is teaching simultaneous localization mapping, laser range finding, robot navigating through a maze, that sort of application. But it's same universities, same price point that we'd be looking to hit, same markets, basically just the one class after your Turtlebot class.
I'm so sorry, I have to cut you off. We're gonna go to the next person, but I have questions I want to ask at the end. So luckily we'll have a little time at the end, and we'll see if Karen ever makes it, but we might end up having even more time depending on if he tunes in. So thank you so much, you guys. We'll go to Yihui. Do you want to get started?
I'm Yihui.
Oh, Yihui, sorry.
Yeah. Glad to see you guys. And I'm currently making open source smart speakers, and it is for makers, for developers. I think we can right now. I can show it to you. What's the state of currently? I use a paper case and use laser cut paper case, and use some and I want to talk about some background. And I'm a software engineer. I worked on microphone array for 3 years, and there are a lot of smart speakers on the market, but none of them are open source. They are black box, and a lot of people have privacy concern of those smart speakers, and we cannot install apps into those smart speakers. So I want to make an open source one. Then we can install all kinds of softwares in it. As smart speakers on the market are already very cheap. If I want to make smart speakers, it's probably not as that cheap. So right now, I just do most of the design to minimize the cost.
All right. I wanted to ask you something about the enclosure. So do you plan to change the design from laser cut plywood or MDF or cardboard to something else, or is this going to be the final material for your project?
Right now, maybe just use papers for the case.
So if someone buys it, wouldn't it be more fragile when you ship it, or what's the plan for protecting it? And also, is it going to be shipped assembled, put together, or are people going to put them together themselves?
Maybe assembled.
All right. So
I'm not sure yet.
All right. So
it's my first time to make a case.
So visually, I'm not saying it's impossible, but it can be a challenge to sell that concept to people, to customers. Now, if you're serious with using cardboard, maybe you can try to focus on the benefits of using cardboard. You know, like probably more environmentally friendly, or you can change the design from time to time. You know, try to give it a spin that makes cardboard a strength and not something that could be seen like a make do approach. You know, so maybe you want to team up with someone who's skillful at graphic design or packaging design, and you know, get it more lively.
Yeah.
Yeah, I agree with that viewpoint. I mean, I think that laser cut paper makes sense on a small scale, but you're going to get really tired of having like to assemble and flat pack. I mean, it just it devalues a really cool product. So I mean, maybe even just like really thin sheet acrylic or something would be enough. And something just to, I mean, it would probably improve the acoustics as well. You know, if that's part of the point, like it's active in the resonance chamber. So I think that, yeah, just trying it out with like maybe mylar or thin sheet acrylic, different materials, and seeing what it sounds like could be interesting, because it could be even that maybe one material is better for bass frequencies, and so someone who's using it to play music prefers that material or something. And I think that that is a good way to add value. You know, alternatively, you're just shipping the electronics and someone somehow cuts out the material themselves. Maybe, I don't know.
Yeah, and definitely. So what we're doing here is a brainstorming, and I will try to be not like too specific on telling you, oh, this is the right way to do things. Not at all. I'll just throw out my ideas out there, and then each one of you is, you know, at the end, the owner of your project. In my personal opinion, I wouldn't put the plywood box or plywood enclosure, MDF enclosure for your project. That I find it very difficult to make it an attractive product on that material. Cardboard, maybe, but as David was saying, maybe you'll have some acoustic issues there. So definitely an interesting concept, an interesting project. The fact that you can use all this, you know, Amazon Echo, Google Home, etc. But there's some work to do with the enclosure, definitely. And well, the good news is that you are in Shenzhen, so you can basically shout a question about manufacturing, and someone will know.
Yeah, the speaker I choose, it has some kind of space for the acoustic part.
Now, one thing to consider, sorry to interrupt, you don't need to have mass manufacturing completely sorted out. You can have your prototype and then make a really good 3D printing version of the final enclosure. Think of, I don't know, maybe you can make it in aluminum, plastic, metal, or cardboard, whichever material you choose. Just try to include the visual aspect of it in your final submission. And the good news also is you still have until August, right? So there's a lot of time for you to really polish this awesome concept.
Cool, thank you. I think we have to keep going. And I'm excited to see Darren has joined us. Welcome, Darren. All right, David, are you ready?
I think I am. Can you guys see me, hear me? Or am I frozen?
I can hear you, but I can't see you. I don't know what happened to the video.
Let's stop, and then, okay.
There we go.
Okay. So I'm David Trutchell. I'm an industrial designer. I just recently graduated last Friday. So
congrats.
either way, yeah, I'm starting my own industrial design practice and doing some other things on the side. And Geometer was my senior capstone project. So the ultimate gist of what it is a library of individual components which can connect to each other in a modular way to create larger scale structures. So instead of just a something on the scale of like 3D printing, we're talking things that are like a chair or maybe even like the frame of a car or tabletop, something like that. So substantially larger. So one of the big problems with like creating a design tool that does this is that, there's different material concerns. Not everyone can create, like they're not a master woodworker or something like that. So we were thinking, oh yeah, I guess my video cut out again. Sorry, I don't have the best internet connection.
I see you.
Okay, cool. So we wanted to lower the barrier to someone saying, I want to make something large scale. So typically if someone wanted to make a chair, they could join a collaborative maker space or something like that and develop carpentry skills. And eventually they would, maybe after 4 or 5 years, make a pretty decent chair. That's not super appealing. It's like this very, very specialized skill. It's not accessible at all. And you may be able to teach yourself CAD pretty easily and maybe design a chair in CAD, but then manufacturing it is almost like impossible without a bunch of other extra skills. So we were thinking we might be able to lower the barrier to entry by essentially putting more constraints on the system and then developing a set of like initial constraints of material minimums and like specific radiuses and things like that. And then saying like, oh, you can only get away with these certain geometric parameters, and ultimately it creates this wireframing structure tool. So, these are like small quarter scale ones, or half scale, excuse me. So with these, they're like toy versions that snap together and recombine. And each one has specific geometry and a name. So a straight piece is module A, and it has an endpoint representation of 0 and 3. So it's 3 inches long. And we can also say that A has 2 ends, 1 and 2. So you can say A1 connects to C3, which might be a 3-pronged part. So if you know that this is prong 3 and this is module C, you can say A1 connects to C3, and then B2 to C1, so on and so forth, to fully describe a design using this reference library. So it's not super intuitive at first, but right now we're sticking with essentially 18 modules. So it actually starts to become fairly repetitive in your mind working with these, trying to make an assembly. So we haven't found that to be a huge barrier as we expected. But essentially we have a limited number of possibilities and configurations, but no bounding limits as far as how many of each individual module you're going to use. So to take something from like a digital reference module that you're making assemblies from, or a half scale set that snaps together, like how do you make a full scale, like workable piece of furniture is like the next step. So we took our modules and we do an offset command and we create thin shell molds. So you have, this is module C, for example, and it has 2 parts and they come together, and then you connect them together using your reference from your assembly, and any castable material can be poured inside of it to then create a solid form. So you can put together a huge network of these things and like make an entire chair in a go. Since we're also using casting, it means that you can embed like electrical wiring, inserts mechanically as far as like rebar. If you have long straight sections, you can tool down wood and put that in between. Right now we've tested casting and mycelium, which is mushroom roots and hemp combined together. And it's really light and it's very strong for what it is. And it looks really cool too. And there's photos on the Hackaday page for that. And then we have concrete and hydrocal, which is a modeling tool, like a modeling substrate. and kind of feels like stone, like artificial stone. So either way, there's like this huge system essentially that allows you to go from like a nothing, know nothing designer to like probably successfully making a chair in less than a week. So how do you distribute this kind of stuff? I mean, obviously the molds are like these thin shell specialized structures. So what we imagine is that maker spaces like NextFab or whatever they have up in near MIT and stuff like that would have a we figure that they would have like a bin of these in their maker space that would just be community owned, and then someone can just make a design, and then as they need to, if they break things while they're like removing the casings from a casting or something, then you can just 3D print new ones on demand. But 3D printing the molds is pretty expensive and really slow and kind of a waste of because you can reuse the molds many times, but still it's definitely not a cost beneficial way of going about this. So it would be interesting to explore casting these individual mold sections. So that's one way of enhancing that. Pricing things out, someone could buy a full set of the actual open-ended molds for around like $300 per set. But that means that if someone makes a design that requires 5 sets, pretty quickly we are talking about the same price as a 3D printer, except that we're talking about a chair, like the ability to make a chair. So it's not super, super unrealistic, but it is still cost prohibitive. So any way that, we can mitigate costs on that end will help people in the long run. That's kind of hard to do without scaling. So that's one end of it. And then the little snap together modules probably have a higher likelihood of like commercial success, if you want to consider it that, because it's seen as a toy. And it's just this interesting thing that you have a toy that if you really, really want to, you can go join a maker space and you can make it real, twice as big. So there might be an appeal to that toy side of it, and from that, there is some precedence. The Tangle Junior product has snap together modules that are like really clean tolerances. And I kind of like using that as a model right now to try and move forward with these little snap together modules. And with those, I could do casting with that, and I need to learning how to do casting molds. But I'm looking, I think longer term for the toy version, it would make sense to do like small scale injection molding. And I have some connections in Philadelphia and stuff for that. And so I'm kind of curious to see where it'll go. It's difficult to tell like how successful it would be because it's such a big project that I haven't really consolidated it into one thing yet. Like here's the mini version product. And so I think people look at the documentation and it's just overwhelming. And so, we have a limited number of likes, we have a lot of views, but I think it just goes over most people's heads really, really quickly. So it might be time to like scale back and say, oh, it's not a solution to world design problems, it's a toy, and to reassure people. I don't know. And that's some of the feedback I got from my peers in my department as well. So
all right,
people have
David.
advice, go ahead.
Sorry,
Yeah.
I'm gonna have Gio maybe take like 2 minutes to give some feedback, and then we'll have to wrap up and see if Darren's back.
Yeah, well, I've been looking at the different parts, and as you said, there are a lot. And if you want to build a chair, you are looking at probably 100 different pieces.
Yeah,
so
easily.
3D printing them is definitely out of the question. I would definitely think that the only way to make this affordable is plastic injection, just like you have in one of your slides, cut in half.
Right.
Now, whoever gets that contract is going to make a killing.
Yeah, they are.
You have quite a number of parts. Now, you don't have to make one mold for each piece. You can put several pieces as long as the mold is balanced. Mold balancing means basically whenever the plastic splits as it's flowing, it covers a very similar volume on both sides. In a nutshell, it's a little bit more complicated than that, but basically, if you put 3 parts to the left and 2 parts to the right that have more or less the same volume, then you can put several in one mold. And yes, probably making the toy version first would be the safest bet. The other thing that I worry about a lot is the structural integrity of the whichever material you cast. If it's concrete, you need some wire or some metal to help. The concrete itself does not make it. Now, if it's going to be resin, sure, resin can be sturdy. You can test it. I don't know, depending on the thickness of your tubes, if it would be enough. But one thing I do know about resin is that it is messy. So whoever is going to cast that, they need to take into account something else, which is the curing time. So when you cast something, and if at the time you're pouring it, it's already becoming solid.
Yeah.
So how are you going to push that resin effectively through that pipes network? You would need vents and some sort of pump. Just to give you an idea, we sometimes make 3D printed molds for resin casting. And sometimes what I have to do when the design is too intricate, I buy one of those huge syringes that are used for cows, and then I just fill it with resin and push it, because if I just pour it, I can't even make it to half the mold by the time it's already solid. So there are a few challenges, not only in the manufacturing, but also in the use for the end consumer that are to address. Not that this is impossible, but it definitely needs some, I would say, user sequence analysis. See how your regular Joe would use it. Someone with not a lot of infrastructure, or a makerspace with not a lot of dedicated space for resin casting or what have you.
Exactly.
Okay. Cool.
Awesome. Thank you, everyone. I don't know what's going on with Darren. He was there for a minute.
Yeah.
But I think we'll go to, oh, he's back? You there? I think you're muted.
Just preventing my, flailing around from taking over video.
Okay, awesome. Go for it, Darren.
Hi, I'm Darren. I'm a longtime Unix guy, hacker. Yeah, I have a mechanical engineering background, but I ended up in software. So I generally just put out whatever ideas I have, and this was the latest, and it should not be here, I don't think, but here we are. So it's a 3D printed hub that you put filaments in, and there's a corresponding transmission that goes with it that is also 3D printed. And so I don't know how this is marketable, really. I mean, because the whole thing is 3D printed, but yeah, I do actually have a couple questions to ask Giovanni. I do want to say, David, I think your idea is cool, and I think it would work really well as like bent metal parts. They could like stick tubes over. It might actually be more scalable, but I don't know. We'll see.
Okay.
So the question for Giovanni is, what do you know about the latest in 3D printer filament and things that I could use to make this better? Because this is just PLA, and if I run it too fast, it's going to like melt, and if I set it out in the sun, it's going to like melt. And ABS is my only other current material other than nylon, but nylon is hard for me to get and more expensive. So what are your opinions?
First of all, I would like to bounce the ball back to you and ask you about the end function of the filler mechanism. I've seen the gallery, but I'm not like 100% sure of what it does. And I'll talk to you extensively about all I know about filament. But first of all, I want to get a clear understanding of the use.
Okay, so basically, a mechanism wheel works by taking the force that is provided to the surface and offsetting it by 45 degrees. Okay. So when you rotate the tire, you end up producing a force that goes this way. Okay. Mechanism wheels require, like 30 bearings and a whole lot of stuff. And usually they're made out of metal and expensive. So I have never ever used them because of that, because they're like outside the range of something I'm going to buy for a project. I don't know, I just had an idea. I was actually trying to make a Mars rover wheel. And, but then I stuck the first set of filaments in and they all went, like this. And so that's all at a 45-degree angle. I realized, oh, that's the same thing that mechanism wheels work on. So here we are.
Got it.
But it's not going to work if you like stick it on a hard surface and like roll it around. It's not going to work because this is going to just slide. But if you like put it out on the grass, it's going to work great because that sliding has a surface to put friction upon.
Okay, cool. Pretty much what I thought. Okay, so one of the most annoying things I found about 3D printing filaments is the high hygroscopy they have, or how much humidity they absorb. And that what that does is that it makes your filament brittle. PLA, one of the most brittle, especially if you are working on a just individual filament perspective. There are other materials that would work a little bit better, but honestly, I think if after some time, especially if it's in contact with grass or outdoors, 3D printing plastic, in my opinion, is not the best choice. I would go for some kind of nylon, maybe. ABA.
Way more hydroscopic.
ABA. Yeah, but not for 3D printing. I'm thinking about, some filaments that are not necessarily for 3D printing. Also, you have ABA. I don't know how elastic it would be. ABA is basically ABS cousin for outdoors. So you might want to try that. But definitely it's a challenge.
I kind of eliminated the injection molding of this because that would be 120 pins to produce the 120 holes,
Yeah.
And that's expensive and complicated.
Oh, yes. Oh, yeah. So, well, I was looking at this morning. Yeah, sorry?
I said, does the interior need to be solid? Because if you just need like the 45-degree thing slightly rounded, there's a potential that you could do like a resin casting or something like that out of a slightly harder material. It would be a little heavier unless you did something to reduce the weight on the inside. But that also might help to make it a little bit more durable. If you just kind of took each of those slots on the inside of that 45-degree angle and filled that with something.
Okay. Yes.
Basically make a turbine.
Yeah, I mean, essentially like a little turbine that you're driving on the ground.
Or you can also make it in two parts so that you have little U-shaped slots. Put the filament in and then close it with another section. That would be super simple, and it could be injected in the same mold probably.
Also, the way like herringbone gears, injection molded herringbone gears are molded, they actually twist the mold off as it comes off. So instead of having a ton of pins making each of those little herringbone fillets, you could have the mold with all the pins in place twist off if the angles on both sides are the same, which strictly speaking they should be. So the act of how the mold is coming off, it's a slightly weird machine, but you could theoretically do it without having all those ridiculous number of pins.
I like Giovanni's idea. Okay, thank you. Though.
One last question. Wait, I forgot. Oh yeah. Is using filament an inherent part of it, or you can go for different? I mean, 3D printed filament, or you can go for other kind of strings.
Yeah, I actually use nylon trimmer line in this because it's a lot stronger and it's a lot more resilient and it's a lot cheaper. You know, so I actually the latest is some guy in Croatia or something like that joined the project, and he's doing it for a school project, and I had the idea of zip ties, and that's in his list of things he can use. So I think that would actually be better because well, it's worse for traction, but better for the springiness in the direction that it's supposed to be.
All right.
Stiffness in the direction that it needs it. So he's going to try that. I haven't gotten to that.
All right, cool. Well, if I may just make one last comment. I know we're about to wrap up. This is a book that I brought here because I wanted to recommend it to you guys. You all are very well versed in manufacturing. There you go. I like that. This is basically like a product design materials class. You know, I know we can get around asking people and Googling stuff ourselves, but this is so easy and so intuitive, and it broadens your mind. It opens your mind so much. So if you have, just like you, David, if you have that book, or if you can get your hands on one of this, I definitely recommend it.